It's kind of incredible to think that humanity has walked on the moon, that when we look up into the sky and we see that glowing ball, that we've been there. And not only have we been there, but we're going back. Now, in addition to all of the people that have walked on the moon, there is a fleet of spacecraft that have orbited the moon, have landed on the moon, roved around the moon, and have taught us a ton about our natural satellite. And one interesting feature on the moon that planetary scientists have found are these sort of long linear structures that are some kind of fault produced by the moon shrinking over time. And recently, we've learned that, in fact, there's a lot more of these across the moon, thousands of them, many more than we had ever expected. And this is telling us a lot about the interior structure of the moon and just how it is cooling down. And that if you were an astronaut on the moon, you would experience moonquakes sometimes, and how this is sort of continuing to tremble and shake the moon. My guest today is Dr. Cole Nypaver. He is a postdoctoral research geologist at the Smithsonian National Air and Space Museum. Cole and his collaborators have been cataloging all of these scarps, these linear features on the moon, where essentially the moon has been contracting and you get this material pushed up into these regions that are visible from orbit. And what this can tell us about the history of the moon and what people going to the moon might experience and where we can learn more about this. So if you want to learn more about lunar geology, enjoy this interview. Cole, the moon, is it dead or is it mostly dead?
I would say it's geologically very active in a fundamentally different way than Earth is geologically active.
Explain more.
Yeah. So basically, Earth, we have a lot of very dynamic geologic processes. We have volcanism, we have aeolian processes, wind-blown processes like Mars, but the moon is affected by fundamentally different processes such as impact cratering and tectonics, which is one of the fundamental aspects of my research is basically how that outer section of the lunar interior, how does that change over time? How does it fracture and break due to internal forces as well?
Now, give me a sense of like how deep you're looking under the surface of the moon.
Right. Yeah. A lot of, these faults that we're identifying in the upper lunar lithosphere, this is sort of in the very outer layer of the lunar interior. That's the crust. This is less than a kilometer deep in most cases. Yeah. Pretty shallow.
And would these, I mean, if it's just less than a kilometer deep, are these visible from the surface? Like, could you find couldn't an astronaut walk into one of these faults and explore it?
Yeah, that's an interesting question. That's precisely how we've found them in the first place, right? So I'm a lunar geomorphologist. So in scanning the lunar surface, I happen to notice these, and many scientists and geomorphologists before me happen to notice these long, sinuous topographic features at the lunar surface. And really the only geologic explanation for a feature like that with positive topography is a subsurface fault structure. And this comes from analogies on Earth, other fault formation features on Earth as well. So yeah, we observe them via high resolution orbital photography and imagery. Apollo 17 was the first time a human being went to a fault feature on another planetary body. They landed in the Taurus-Littrow Valley, which is cross-cut by exactly one of these features that I'm referring to. These relatively shallow fault structures. It's known as the Lee-Lincoln Scarp, right? So once that happens, a number of planetary scientists took that and sort of started looking for other analogous morphological features across the lunar surface. And at first, they found tens of them, all throughout the lunar highlands. Then digging a little bit deeper with some improved high-resolution imagery from the Lunar Reconnaissance Orbiter camera, researchers started to find thousands of these features, all ubiquitous across the lunar surface. Now, those were primarily concentrated in the lunar highlands, which are sort of the very, when you look up at the moon at night, they're very high albedo, very bright terrains, very optically very rough, a lot of topography. But until recently, those types of features, these fault features, weren't really identified in the Maria, which is sort of the dark spots that you see when you look up at the moon. Those are these voluminous outpourings of flood basalts that formed between 3.8 and 1.2 billion years ago at the lunar surface. So recently, we've been looking in those terrains, and we found sort of an equivalent number of these fault structures. And now, by doing that, we've sort of now have a globally complete perspective on recent lunar tectonics and fault formation in the upper lunar lithosphere.
Now, I've walked in a fault in Iceland. There's this place where it's like the continental divide. You can go and walk in this steep cliffs on both sides, and there's the area is like breaking apart, and various weathering processes is happening on it. But with the moon, are these getting filled in by the regolith that's constantly kind of raining back down from all of the impacts? So they're not, that it took more careful observations to be able to actually find them?
Yeah, that's a fascinating question. So that gets at lunar surface evolution, which is something I'm particularly interested in my own research. So these features, the reason we've identified them as being geologically young, that is to say hundreds of millions of years old. I know that doesn't sound young, but in geologic time, the moon is 4.4 billion years old. So hundreds of millions of years is pretty young. The reason we've identified them as being geologically young is because they're morphologically undegraded. They're crisp, right? When you look at the lunar surface, one of the most compelling features is not a morphologic feature, but just the fact that everything is rounded, right? Like there's no, if you look at something like the Grand Tetons or the Himalayas, they're very sharp, very jagged mountain ranges. When you look at the surface of the moon, everything is very rounded. That is because of the process that you asked about, which is sort of this regolith raining down via macroscopic space weathering. So the moon lacks even a thin atmosphere with which to protect itself from impactors of all sizes. So from sand-sized micrometeoroids up to large asteroids colliding with the lunar surface. And those processes basically act to churn the lunar regolith, which is the lunar soil, this amalgamation of fine-grained material and fragmented breccias and rocks. And over time, that churning actually reduces basically crisp topography down to sort of rounded terrain that we see. And that process does fill in, these elongated fault features that we see to some degree. So if you see a feature that is not degraded, not rounded, your mind immediately jumps to, oh, this is geologically young. This is undegraded, and it hasn't been around for a long time.
It's interesting. I wonder if that's sort of like the sniff test you can use if you're watching some movie about people being on the moon. And if there's like jagged mountains around them, you're like, no, someone didn't do their research. No, it should all just like smooth, wavy hills.
Yeah.
And when you look in the Apollo footage, for sure, that's what you see. All the mountains around them, everything is just wavy hills.
Exactly. Yeah. I mean, the exception is, again, features like what we're seeing, these very crisp morphologic surface expressions of shallow thrust faults, but also impact craters, very recently formed geologically young impact craters are also very crisp topography, right? Like they have very sharp crater rims and very sharp contacts and very distinct crater floors. So anytime you see that, and over time that like crisp, that nice clean morphology subsequently becomes degraded to basically a topographically muted expression that's barely visible to the human eye.
So, here on Earth, we have plate tectonics. That is driving the faults that we experience. I live on the west coast of Canada, and we are made very aware of the faults that are all around us. So what is the process that is creating and driving faults on the moon?
Yeah, well, so you're absolutely right. So plate tectonics on Earth drives fault formation of all kinds, right? At plate boundaries, you have these continental plates and oceanic plates, which are either coming together, moving apart, or sliding past one another. And those are the three primary types of faults. You have normal faults where you have these slabs of rock sliding away from each other. You have thrust faults where they're being pressed together and riding up over one another. And then you have places like the San Andreas faults where the rock is actually sliding past each other horizontally in the X or Y axis. And that's all driven by plate tectonics. But on the moon, that is actually not the case. So plate tectonics is actually a very interesting phenomenon in our solar system in that we are the only silicate solid body that has it. Pretty much every other solid body and moon in our solar system does not exhibit signs of plate tectonics. The moon, our Earth's moon, for example, is what's called a one-plate body or a stagnant lid tectonic body. And that is basically you have one complete outer shell that is the lunar crust that doesn't have these sort of seams like the Earth does along these plate boundaries. It is just one complete crust. And the deformation mechanism, the reason these faults are forming on the moon is because of global contraction. So the moon is very slowly, very subtly shrinking. And there hasn't been a lot of shrinkage. This is called global contraction. There hasn't been a lot of global contraction. Throughout lunar history, we're talking tens of meters of radius change. But it is enough to cause a global network of these shallow thrust faults.
Wow. And I'm sort of imagining, like, if the moon is getting a little bit smaller by tens of meters, then that energy has to go somewhere. And so you're getting these kinds of cracks that are sort of opening up as I guess more material is trying to fill a smaller volume.
Yeah. Well, actually, it's going the other way. So they're not opening up; they're actually being pressed together. So these are thrust faults. So basically, you're losing volume as the lunar interior cools and as this global contraction occurs, and that loss of volume has to be accommodated some way, and it's actually accommodated in the z-axis. So these faults form whenever basically some of the lunar crust rides up over another section of the lunar crust in very isolated occurrences that are isotropically distributed across the lunar surface. So yeah, these are thrust faults, and it's the stresses we're talking about from global contraction are tens to maybe even hundreds of megapascals. So it's not insignificant either. It's quite a driving stress mechanism. And there's also overprinting. I mean, so global contraction is the primary stress mechanism responsible for the formation of these faults, but you also have some interesting stresses acting on the lunar lithosphere from tidal interactions between Earth and the moon. Yeah, so it's not important not to forget about those, right? So they're relative to global contraction. The stresses associated are relatively minor, megapascals, if not kilopascals in many cases. But you want to think about things like orbital recession. So as I'm sure you're aware, I'm sure much of your audience is aware, the moon is migrating slowly away from Earth in its orbit, very slowly, but it's enough to cause relaxation of the near-side tidal bulge on the moon. So basically, the Earth's tug on the moon is causing this near-side bulge. Again, we know this via basically laser reflectivity off of the near side of the lunar surface. And that bulge is not a lot. There's not a lot of a signature there, but as the moon migrates away from Earth in its orbit, that bulge relaxes, and you get a compressional stress on the near side as well. And then you also have a non-circular orbit around Earth, which causes stresses at perigee and apogee in that orbit. So again, those actually influence the orientation pattern of the faults that form, but they don't actually cause the fault formation in and of itself. Yeah.
And I guess if the moon wasn't tidally locked to the Earth, then it would be even more significant because that bulge would be moving, shifting.
Yeah. Well, exactly. And these tidal stresses you can compare with something like Io, or let's take Io for example, right? It's the eccentricity. The eccentricity of that orbit is enough to actually cause basically a fully molten interior and volcanism. Like that is an incredible amount of stress associated with that orbital eccentricity, the perigee and apogee. So it's we don't have anything. The moon doesn't have anything to that degree, but it's a similar stress mechanism.
Right. That if we went further, that if the Earth was, hundreds of times more massive, then we might start to have a more significant effect on the moon.
Sure.
So, hopefully we're going to have humans set foot on the moon, and over the long term, hopefully there'll be some kind of permanent human presence on the moon. Should the astronauts working at the base, will they experience moonquakes?
Yeah, well, that's a great question. So, I will preface this by saying that I think that moon we know moonquakes occur, and I'll explain how we know that. But I would say that the scientific value of the moonquakes far exceeds the danger of them.
Right.
Yeah,
Yeah.
but
Well, I'm not saying they should be worried about them. More
yeah,
just would they even experience them?
yeah, it's certainly possible, right? So we can go back to the Apollo program. So between 1969 and 1977, the Apollo Lunar Seismic Package, which was a series of seismometers set on the lunar surface by the Apollo astronauts, that experiment package detected about over 13,000 seismic events in the lunar interior. Now, those aren't all violent moonquakes. In fact, the vast majority were very subtle events. Most of them were labeled as what are known as deep moonquakes. So these are if seismic events that occurred sort of at the core mantle boundary in the lunar interior, very deep. The other larger percentage of them were seismic events from impacts. So they could detect asteroids and meteoroids colliding with the lunar surface at 17,000 plus kilometers per second. Now, that said, 28 of those seismic events were shallow moonquakes with pretty significant magnitudes, pretty significant shaking associated with them. And now the leading hypothesis is that those shallow moonquakes, those 28, were associated with fault formation in the upper lunar lithosphere. So basically the formation or the slip associated with these faults. So when you have those bodies of rock sliding past one another, that releases a tremendous amount of energy, and that energy manifests at the surface as a moonquake, shaking in the horizontal and vertical direction. So it's certainly possible that if you are on the surface near one of these features, that could happen. But when you do some quick statistical math, 28 shallow moonquakes over the course of 8 years. Is not a high recurrence interval, and the likelihood of any one of those happening in a specific location is even less so. So it's but yeah, the answer to your question is yes, it's possible. And these types of features, these faults, are something that you need to be considerate of when thinking about a long-term lunar outpost or any sort of long-term habitation, for sure.
Yeah, we had done some reporting on Universe Today about boulders that have been seen recently. You can see the track of it rolling downhill. And so some force is knocking them off of the side of a crater rim and having them roll downhill.
Most certainly. Yeah, it could very well be shallow moonquakes from fault slip, from fault formation. There's a recent paper came out last year in 2025 that documented basically in the Taurus Littrow Valley in the Apollo 17 landing site, if there happened to be a magnitude 3 earthquake form in association with that feature, what would be the geomorphic effects of that event, right? And there happened to be a lot of, as you're saying, boulder falls and landslide material in the Taurus Littrow Valley. And interestingly enough, all of those materials coincide temporally with the formation age of the Lee Lincoln Scarp, right? So there's a very interesting coincidence there. And that paper showed that it was published in Science Advances, actually. It showed that the shaking associated with that event would be more than enough to topple those rocks and to cause that big landslide off the South Massif in the Taurus Littrow Valley. So yeah, all those geomorphic effects are considerable, and there's a magnitude 3 a moonquake would be certainly more than enough to cause them.
Mm-hmm. Now, one of the things that's really fascinating about the moon when we look at the near side compared to the far side is totally different feature, totally different landscape. The near side with its lunar highlands and the mare, and then on the far side, it just looks crater pounded. Has your work tried to help explain this strange asymmetry on the moon?
Yeah, that's an interesting question. So that asymmetry is definitely something that has been of interest to lunar scientists since we've been returning images of the far side, right? All the way back to the Luna missions, to the Lunar Orbiter program as well. It says actually here, so what you're describing is basically, so the near side is what you see when you look up at the moon. This is basically the near side here. And then on the far side, you spin this around, and you really don't see those dark mare patches, right? Now, the hypothesis here is that you have a much thicker lithosphere on the far side, and a relatively thinner lithosphere on the near side. Now, the faults that we're identifying don't quite get to the depth of the base of the highlands lithosphere. So it's hard for us to constrain the thickness of the far side versus near side lithosphere. That said, there are some features. There is basically a theory out there that the lobate scarps, these features that form this, that's the geologic term for them in the lunar highlands. The length of them, basically the longer features, are proportional to the thickness of the lithosphere. Now, that's an interesting question. I don't think it's been tested at depth, but it is certainly possible that we could use some of the morphometric parameters of these faults and of these features to get a better understanding of the lithospheric thickness. Yeah.
Do we see the faults on both hemispheres?
Absolutely, yeah. So they're globally ubiquitous. So they're all over the place, even at the South Pole, North Pole, throughout the near side Maria. All over the place.
Is there, okay, so if you could plan your own mission to the moon and you could send some astronauts and maybe, send some more Harrison Schmitts, like some actual geologists, where would you want them to go? Do you have like one place where you're like, oh, I really wish I could get boots on the ground right there?
Yeah, well, I think the South Pole is incredibly compelling from a volatile standpoint, right? I think that's the correct decision, and there's good reason to go there in upcoming lunar missions. But
yeah, sure, fine. But I want to know.
Standpoint.
Yeah. I want to know. Get your hands into those faults and learn more.
Really. So the problem that I see is that we don't really have good constraints on how a fault forms in a planetary regolith. We know that they're there. We have some very, very preliminary modeling done that demonstrates that these are shallow thrust faults, right? They are what we think they are. But exactly what does that look like on the micro scale? We don't have a good idea. So what I would like to do is get to the moon with a ground penetrating radar or a seismic suite that would give me some sort of subsurface imaging to look at these faults. And if we can get an understanding, if we can constrain what these faults look like in the subsurface, then we can basically constrain recent lunar thermal history, because observationally, these features are used to better understanding how much, as we've talked about, how much global contraction has taken place. What is the rate at which, and amount at which the lunar interior is cooling? What is the rate at which lunar contraction is occurring? That is loosely based on the geometry of these faults. And if we can get better constraints on those geometries, we can get better constraints on lunar thermal history as a whole. So, there's a lot of these all over. There's over 10,000 of these fault features that we've identified to date. So, on the near side in the Maria, I would say that's probably my preferred location to go look at one, because you can sample. You can not only look at tectonic features and constrained fault geometry, but you can sample volcanic history. You can sample really interesting volcanic materials as well as target tectonic features. So there's a lot of options.
Next time we come around with our checkbook, you need a fast answer. You're like, right here. I think there's aliens right here.
I like it all. Yeah, it's all. Yeah. Every area on the lunar surface is interesting to me.
I mean, one of the most fascinating piece of research that we saw from the Chinese Chang'e missions was they had these ground penetrating radar instruments on board the rovers, and they were able to sort of see this slice down through the top of the regolith, and you could see the particle size. So the top, it's like this talcum powder, and then as you go down, they just turn into larger and larger boulders all the way down. And so like those instruments exist. And so I can imagine, like if you could do a comparison, take one of those across one of these fault lines and map it out, how deep does it go? How wide does it go? Compare that to just a random spot on the surface of the moon.
It would be fascinating. Yeah. The Chang'e rovers really placed very important constraints on the regolith structure in general. So it's another longstanding question is in the subsurface, in highlands material versus lunar mare terrains, what does the lunar regolith look like as you go down? Not just in the context of tectonics and fault, but in general. As I mentioned, the lunar surface has been subject to 4+ billion years of constant impact bombardment. So, how far down is the bedrock? Is there even bedrock? These are all really interesting questions that we have yet to answer.
Now, this is just one object in the solar system and, something that you've been analyzing quite carefully. But when you think sort of larger picture across the solar system, Mercury, and even some of the sort of cryovolcanism and stuff that's happening on places like Europa and what's happening on Io and stuff. Are there other worlds that you feel would be an interesting comparison? Venus? Like Venus must have these things too, right?
Venus is fascinating from a tectonic point of view. So it's, we don't have the best, I hesitate to call it image data because it's actually synthetic aperture radar data. So we don't have the best perspective on what's going on at the Venusian surface right now. It's those data are somewhat coarse resolution. They're from the data from the 90s. So it's really going to be really important to get higher resolution image or radar data of the Venusian surface to help better constrain these things. But tectonically, there's all kinds of crazy stuff going on at the surface of Venus and in the shallow subsurface. You're probably familiar, but there are these large coronae type features, these large circular tectonic rings, basically, that are the surface expression of magmatic upwelling. So the magma actually comes from the Venusian interior, presses up on the Venusian crust, and then relaxes, and you're left with this ring of fault features. You have large plains, which are just modeled with these ridge-like features that form via large-scale compression. It's really interesting, and it would help us constraining tectonic activity on Venus and any of the other planetary bodies you mentioned would be really helpful for understanding basically silicate body formation across the entire solar system. I mean, Mercury is a great analogy to the moon as well. It's the same processes that I'm describing on the moon have taken place on Mercury to a much larger scale. So more mass, more internal heat, more global contraction, bigger faults, more faults. All of it's like the moon's bigger brother in tectonically.
Yeah. I know there's these like weird kind of chaotic spider terrain where you're seeing these fault lines, and they're a lot more kind of exposed and really look like, I don't know, spider webs almost.
So you're referring to Venus?
No, I was talking about Mercury.
Oh, yeah. There's a lot of really interesting features that I think could use some further investigation. And it would really help us understand how this type of one plate body tectonics, the stagnant lid tectonics process works.
Yeah. Well, I'd like to shift gears now and talk about sort of, you mentioned before we were recording that you're starting to sort of think about boulders on the moon. So give me a sense of what you're investigating.
Yeah, it's one of the things I'm really interested in recently is surface rock size frequency distributions on the moon. So the moon is just covered with rocks. There's no really outcrops like we see on Earth. You don't have any nice road cuts where you see nice layering of sedimentary deposits. Really, all you're left with is just a distribution of meter scale and sub-meter scale, centimeter scale rocks all over the place. And those rocks originate from different sources. They're frequently excavated by impacts. Impact craters collide with the lunar surface, and they throw up hundreds and thousands of, even tens of thousands of rocks and boulders, depending on the size of the impact. So one interesting question is, what is influencing the amount and distribution of boulders at the lunar surface? Where do those processes vary in the lunar subsurface that could be controlling that? And how long are those boulders present? How long are those rocks present at the lunar surface? What's their lifetime, given the intense micrometeoroid bombardment that occurs at the lunar surface?
So that same process that's wearing down the hills is wearing down just individual rocks and boulders on the surface of the moon.
Very similar processes. There's some subtle differences. So these rocks are very competent bodies of mass, right? They're solid material. So it's predominantly the stress, the mechanisms responsible for breaking down the boulders are, one, micrometeoroid bombardment, sandblasting from very high velocity asteroids, basically. It's very tiny ones. And also thermal fatigue. So the moon has very intense day-night cycles, 14 Earth day days, 14 Earth day nights. The temperature fluctuations are immense, and that actually can expand and contract and break the boulders in and of itself. The relative contribution of those two processes to rock breakdown on the lunar surface is not well constrained at the present, but we know that both are occurring. Now, topography evolution that we were talking about earlier, that sort of hill slope diffusion, is actually predominantly caused by secondary ejecta, mantling. So you have a big impact that forms over here, it throws material over here, and in addition to the micrometeorite bombardment that we talked about, that sort of secondary ejecta, that secondary impact cratering, influences local topography as well. So they're very similar mechanisms. But yeah, again, anything at the lunar surface is subject to pretty intense weathering patterns.
Now, would you, without an atmosphere, you would never find solid meteorites in the way that we find them on Earth and the way they've been seen on Mars, would you?
It's really difficult to find them simply because of the energies associated with the impact crater formation process, right? So a lot of times those micrometeoroids, those even larger impactors, vaporize upon impact with the lunar surface. They don't slow down. They
Right.
as you mentioned, yeah, right. So they hit with a lot of energy. So you get predominantly vaporization of the bolide of the impactor. You get vaporization of the target material. And as those shock waves of the impact dissipate into the lunar interior, into the lunar subsurface, you get melting of rock, that melts, actually recoagulates and resolidifies into what's called a breccia, which is pretty much the dominant rock type at the lunar surface, is impact breccia, which tells you something about how much impact cratering has gone on at the lunar surface. And then even beneath that, you get a lot of fracturing and breaking of the subsurface rock. That's why I questioned the term bedrock as it relates to the moon earlier, is because any bedrock would have been deposited billions of years ago and has been subject to this impact cratering process ever since.
Right. Just constantly being kneaded and pounded, and who knows what's left.
Constantly.
But it's interesting that if you were walking along the surface of the moon and you were looking for a pebble that had recently hit the surface of the moon, it would vaporize and you would get like a tiny little crater.
For the most,
that would be the only evidence
exactly
that this had happened.
Yeah. You would only see a crater. You really wouldn't see a bunch of little asteroids laying on the lunar surface. And what you might see, actually, that vaporization, that material basically comes out of the gas phase and actually re-solidifies on lunar, like grains of material in the lunar regolith. This is where what are called nanophase iron particles come from. And I know you had Kevin Cannon on to talk about that a while back, but you get these little agglutinates, basically is what they're called. They're little grains of regolith material that are covered with nanophase iron that has precipitated from impacts as that material vaporized. So it's one of the main components of regolith in and of itself. It's glass, nanophase iron agglutinates, and breccia for the most part.
Right. Yeah, it'll be great if we can actually have a permanent base on the moon where astronauts are going outside and they're examining these kinds of features and finding interesting examples of different phases of different sizes, because there's only so much that the Apollo astronauts could do in the limited time that they had with the vehicles that they had available to them. And there's got to be so many more really interesting places to go, even within walking distance or driving distance of wherever the base is going to be, from the the permanently shadowed craters to some of these boulders and rocks and ejecta and recent sites. I think it would be fascinating for them to find just like a little tiny crater.
Just a little one,
small that hit the moon.
Well, I mean, the best resolution image data that we have from orbit is about half a meter per pixel. And you're not even going to see small impact craters on the size scale that you're referring to in those data. So there's a lot of sub-resolution geology to be done. That's really important for constraining a lot of these regolith and impact cratering processes. And it also highlights what you're mentioning, the importance of selecting the right landing site, right? So you want to make sure, this is why so much thought goes into this. You want to make sure that the rocks you're sampling and the geology you do answers fundamental questions about lunar geologic history and solar system geologic history, solar system formation, right? And you can do that with samples from the lunar surface if you pick up the right rocks.
Right. Cole, question I ask all my guests: what are you obsessed with right now?
Yeah, we touched on it a little bit, but constraining these rock size frequency distributions and really constraining this macroscopic structure of the regolith, right? Like what is the lifetime of a rock at the lunar surface? What is the origin of those lunar surface rocks? What is the structure as you go down with depth? How does regolith change?
But is there is there like a surprising hunch that you have? Like, is there something that's kind of making you wonder if there's something that we're missing or something that maybe we have yet to uncover?
You mean in with regards to lunar regolith or the moon as a whole?
or just just the process of being obsessed with things, like for me, my obsessions come from where do I feel is kind of a gap in my knowledge, or something that I feel is like a gap in everyone's knowledge. Like there's something that doesn't seem to be resolved, and that and it nags at my brain.
Yeah.
And I have to keep thinking about it,
I mean, that's where yeah, go ahead.
I'll just say, before it sort of assembles into something more coherent and concrete, it sort of exists in this cloud in my brain that keeps diverting my attention to this subject. And that's sort of, that's how it manifests for me.
I know exactly what you're talking about. I mean, that happens. So yes, that has happened recently in the context of, this lunar rock and lunar regolith investigation and project that I'm working on. But this is how I came upon my research with lunar tectonics and fault formation. I was really obsessed with these papers from the Apollo era on the Lee Lincoln Scarp and the Taurus Littrow Valley, and I was really obsessed with all these papers on these faults in the lunar highlands, and I was reading them and trying to understand them. And I came to the realization that these are all describing fault features in the highlands, which is 83% of the lunar surface. And there were no fault features, no geologically fault features described in the other 17% of the lunar surface, which is made up of the lunar maria. So that really drove me crazy. So I started looking for them, and my goodness, did we find them? We found thousands of them across the lunar maria that hadn't been described previously. So it's an interesting story, and I don't think it's over yet. I think there's a lot to learn about lunar tectonics and lunar tectonism in general. I will say that similar story is also playing out in my mind right now in the context of regolith, specifically on the lunar maria deposits. There's a hypothesis out there that protolith, basically the mechanical properties of the substrate, of the basalt itself, the mineralogic properties of it, can control how many rocks are produced whenever that protolith is impacted by an asteroid or meteoroid of some kind, right? That's an interesting hypothesis, and it's one that I'm really interested to test, because the other competing hypothesis there is that, you have an older surface on which regolith accumulates over time. That kind of intuitive, right? You have a rock that is continually turned into regolith. The more impact bombardment that rock is exposed to, the more regolith accumulates on top of it. That regolith then inhibits the amount of rock production that it can occur when the substrate is impacted. But if protolith properties actually control surface rock populations and rock production on the moon, then that throws a whole new series of variables into the equation. So in other words, it's not just a direct correlation between surface rock populations and age. It then becomes, a correlation between surface rock populations, age, and the geochemistry of the underlying basalts, which is really an interesting question to answer.
Well, you gave me a new word, protolith.
Oh, it's a great word. Yeah.
Yeah. I hadn't heard that one before, but essentially it's like it was whatever was the original volcanic flow that created the material that then got pounded up.
Exactly.
So,
yeah.
Right. Yeah,
and
that's interesting.
And I mean, that logic follows, right? Like an older Mare basalt flow has been subject to more bombardment. Therefore, it should develop more regolith on top of that particular protolith. And a younger Mare basalt flow should have accumulated less regolith overlying. But it may not always be the case.
Yeah. It's a fascinating time, and it's, we're standing here now just a handful of years away from this resurgence of missions to the moon, whether it be from the Chinese, whether it be from private space flight like SpaceX, or whether, it's NASA's Artemis missions. We're going back to the moon, and hopefully we'll find out a lot more information. Cole, thank you so much for your time, and good luck with your research.
Thank you so much. I appreciate you having me on.
I hope you enjoyed this interview about the geology on the moon. I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Bear Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Bela, Cooper and Ellie, Dark Finga, David Giltonen, David Matz, Evan.pro, Greg Feely, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Josh Schultz, Marcel Smits, Michael Purcell, Nordspace, OneStepForAnimals.org, Paul Buck, Rankaidu, Richard Williams, Sean Sargent, Stephen Feinler Munley, Team 49, Telescopes Canada, Wolfgang Klotz, and Zeldebor Galactic Defender, who support us at the Master of the Universe level, and all our patrons. All your support means universe to us. Man, I am so excited about humanity returning to the moon. And I don't care how. If the Chinese do it, if NASA does it, if private spaceflight does it, then that's going to be incredible. That we will be able to look up into the sky and know that there is a permanent human presence on the moon, in the same way that we look into the sky and we see the International Space Station fly overhead. And there are astronauts up there looking back at us. And the moon is so accessible compared to every other place in the solar system. And yet has gone through the same kind of history that the other worlds have, that Mercury, that Venus, that Mars, all of these worlds have gone through this history and are continuing to go through this history. And a lot of the secrets that we have are available to us just there on the moon. And we just need to go back. But even if we don't set foot, we can still learn a ton from sending landers, rovers, and orbiters to the moon. All right. We'll see you next time.